The requirement for ground fault circuit interrupter, or GFCI, protection of outdoor receptacles in commercial applications is a safety measure intended to reduce the risk of electrical shock. However, there are some exceptions to this requirement, including firstly, receptacles that are not readily accessible to the public, secondly, receptacles that are used for industrial machinery or equipment, and thirdly, receptacles that are used for the servicing of vehicles. The rationale for these exceptions is that the risk of electrical shock is lower in these situations. For example, receptacles that are used for the servicing of vehicles are typically located in areas that are not readily accessible to the public, and they are typically used by trained professionals who are aware of the potential hazards. Even though GFCI protection is not required in this case, it is still a good idea to use GFCI protected receptacles whenever possible. GFCIs can help to prevent electrical shock, and they can also help to protect against electrical fires. Examining the specific requirements within the National Electrical Code, or NEC, is crucial for understanding the application of GFCI protection. The NEC outlines specific instances where GFCI protection is mandatory, permissible, or not required. For outdoor receptacles, the general rule necessitates GFCI protection to enhance safety against electrical hazards in damp or wet locations. However, as previously stated, exceptions exist particularly for receptacles dedicated to specific purposes or located in restricted access areas. When dealing with commercial vehicle servicing areas, the NEC allows for exceptions, provided certain conditions are met. Firstly, the receptacles must be dedicated to vehicle servicing, implying that they are intended solely for powering equipment used in the maintenance or repair of vehicles. Secondly, the area where these receptacles are installed should not be readily accessible to the general public. This condition aims to limit exposure to potential electrical hazards to trained personnel who are familiar with the equipment and safety procedures. It's essential to recognize that these exceptions are not blanket waivers of safety precautions. Instead, they reflect a risk-based approach where the likelihood of electrical shock is deemed low due to controlled access and trained personnel. Nonetheless, it's prudent to consider incorporating GFCI protection even when not strictly mandated by code, as it offers an additional layer of safety. GFCI devices continuously monitor the current flowing through a circuit. If a ground fault is detected, indicating that current is leaking to ground, the GFCI trips and interrupts the power supply within milliseconds. This rapid response can prevent severe electrical shock and minimize the risk of electrical fires. Moreover, advancements in GFCI technology have significantly improved their reliability and reduced nuisance tripping. Modern GFCIs are less prone to false alarms caused by minor voltage fluctuations or electromagnetic interference. This enhanced performance makes them more suitable for use in various applications, including those where they were previously considered impractical. When evaluating the decision to use or not use GFCI protection for outdoor receptacles in commercial vehicle servicing areas, it's imperative to conduct a thorough risk assessment. Factors to consider include firstly, the proximity of the receptacles to wet or damp locations, secondly, the likelihood of exposure to corrosive substances, thirdly, the level of training and awareness of personnel using the equipment, and fourthly, the potential consequences of an electrical shock incident. Based on this assessment, a determination can be made regarding the necessity of GFCI protection taking into account both code compliance and safety considerations. Furthermore, it's important to stay informed about updates and revisions to the NEC, as well as local electrical codes and regulations. These codes are periodically updated to reflect advancements in technology and evolving safety standards. Consulting with qualified electrical engineers or inspectors can provide valuable insights into interpreting and applying these codes correctly. In addition to GFCI protection, other safety measures should be implemented to minimize electrical hazards in commercial vehicle servicing areas. These measures may include firstly, regular inspection and maintenance of electrical equipment, secondly, proper grounding and bonding of metal enclosures, thirdly, use of weatherproof enclosures for outdoor receptacles, fourthly, provision of adequate lighting to enhance visibility, and fifthly, implementation of lockout/tagout procedures for equipment maintenance. By combining GFCI protection with these complementary safety measures, a comprehensive approach to electrical safety can be achieved, ensuring the well-being of personnel and minimizing the risk of electrical incidents. It is worth reiterating that while code compliance is essential, it should not be the sole basis for determining safety practices. A proactive approach to risk management, incorporating both code requirements and best practices, is crucial for creating a safe working environment. In summary, the decision to use or not use GFCI protection for outdoor receptacles in commercial vehicle servicing areas should be based on a careful evaluation of code requirements, risk factors, and safety considerations. While exceptions to GFCI requirements may exist, it's prudent to consider incorporating GFCI protection whenever possible, as it provides an additional layer of safety against electrical shock and fire hazards. Moreover, a comprehensive approach to electrical safety, encompassing regular inspection, maintenance, and adherence to best practices, is essential for minimizing electrical hazards in commercial environments. The National Electrical Code, or NEC, serves as the foundational standard for electrical safety in the United States. It provides comprehensive guidelines and requirements for electrical installations, including those involving outdoor receptacles in commercial settings. Understanding the NEC provisions regarding GFCI protection is crucial for ensuring compliance and minimizing electrical hazards. The NEC mandates GFCI protection for 125-volt, 15-amp and 20-amp receptacles installed in specific locations, including those in dwelling units in certain areas of commercial establishments. These requirements aim to protect individuals from electrical shock hazards in environments where the risk of contact with water or other conductive materials is elevated. However, the NEC also recognizes exceptions to these GFCI requirements, particularly for receptacles used for specific purposes or located in areas with restricted access. One such exception applies to receptacles used for the servicing of vehicles, as mentioned earlier. The rationale behind this exception is that these receptacles are typically used by trained personnel who are familiar with the equipment and safety procedures. Additionally, the areas where these receptacles are installed are often not readily accessible to the general public, further reducing the risk of accidental contact with energized parts. While the NEC permits exceptions to GFCI requirements in certain cases, it also emphasizes the importance of conducting a thorough risk assessment to determine the appropriate level of protection. Factors to consider include firstly, the likelihood of exposure to wet or damp conditions, secondly, the presence of conductive materials, thirdly, the level of training and awareness of personnel using the equipment, and fourthly, the potential consequences of an electrical shock incident. Based on this assessment, a determination can be made regarding the necessity of GFCI protection, even if it is not strictly mandated by the NEC. In addition to GFCI protection, the NEC also addresses other safety measures related to outdoor receptacles, such as the use of weatherproof enclosures, proper grounding and bonding, and overcurrent protection. Weatherproof enclosures are designed to protect receptacles from exposure to rain, snow, and other environmental elements, reducing the risk of corrosion and electrical faults. Grounding and bonding ensure that metal parts of the electrical system are properly connected to ground, providing a low impedance path for fault current to flow back to the source. Overcurrent protection devices, such as circuit breakers and fuses, are designed to interrupt the flow of electricity in the event of an overload or short circuit, preventing damage to equipment and reducing the risk of electrical fires. When installing outdoor receptacles in commercial settings, it's essential to follow the NEC guidelines for wiring methods, conductor sizing, and equipment installation. Wiring methods refer to the types of cables or conduits used to run electrical conductors, while conductor sizing refers to the appropriate gauge of wire for carrying a specific amount of current. Proper equipment installation ensures that receptacles and other electrical components are securely mounted and properly connected to the electrical system. Furthermore, it's important to ensure that all electrical work is performed by qualified and licensed electricians who are familiar with the NEC and local electrical codes. Hiring qualified professionals can help to ensure that the electrical system is installed safely and correctly, reducing the risk of electrical hazards and code violations. It is crucial to stay up to date with the latest edition of the NEC and any amendments or interpretations issued by local authorities. The NEC is revised every 3 years to reflect advancements in technology and evolving safety standards. Staying informed about these changes can help to ensure that electrical installations comply with the latest requirements. In summary, the National Electrical Code, or NEC, provides comprehensive guidelines for electrical safety, including those related to outdoor receptacles in commercial settings. While the NEC permits exceptions to GFCI requirements in certain cases, it emphasizes the importance of conducting a thorough risk assessment and implementing appropriate safety measures. By following the NEC guidelines and working with qualified professionals, it is possible to minimize electrical hazards and ensure a safe electrical environment. Examining the specific context of vehicle servicing applications, it is important to consider the potential hazards associated with exposure to water, chemicals, and mechanical damage. Vehicles undergoing maintenance or repair may be exposed to water from washing or cleaning operations, as well as chemicals such as solvents, oils, and antifreeze. These substances can compromise the insulation of electrical equipment and increase the risk of electrical shock. Additionally, vehicle servicing areas may be subject to mechanical damage from tools, equipment, or vehicle movement, which can damage electrical wiring and enclosures. Given these potential hazards, it is prudent to implement additional safety measures beyond those strictly required by the NEC. These measures may include, firstly, the use of corrosion-resistant receptacles and enclosures, secondly, the installation of physical barriers to protect receptacles from mechanical damage, thirdly, the provision of ground fault monitoring systems to detect insulation failures, and fourthly, the implementation of regular inspection and testing programs to identify and address potential hazards. Corrosion-resistant receptacles and enclosures are designed to withstand exposure to moisture, chemicals, and other corrosive substances, reducing the risk of electrical faults and equipment failure. Physical barriers, such as bollards or guardrails, can protect receptacles from being struck by vehicles or equipment, preventing damage to wiring and enclosures. Ground fault monitoring systems continuously monitor the insulation resistance of electrical circuits and provide an alarm if a ground fault is detected, allowing for prompt corrective action to be taken. Regular inspection and testing programs can help to identify and address potential hazards before they result in accidents or equipment failures. These programs may include visual inspections, insulation resistance testing, and ground impedance testing. In addition to these physical safety measures, it is also important to provide adequate training and education to personnel working in vehicle servicing areas. Training should cover topics such as electrical safety procedures, hazard recognition, and the proper use of personal protective equipment, or PPE. Personnel should be trained to recognize potential electrical hazards such as frayed wiring, damaged receptacles, and wet or damp conditions. They should also be trained to use personal protective equipment, such as rubber gloves and insulated tools, when working with electrical equipment. Furthermore, it is important to establish clear communication channels and reporting procedures for electrical safety concerns. Personnel should be encouraged to report any potential hazards or safety violations to the supervisors or safety officers. This can help to ensure that problems are addressed promptly and that a safe working environment is maintained. In summary, vehicle servicing applications present unique electrical safety challenges due to the potential for exposure to water, chemicals, and mechanical damage. While the NEC permits exceptions to GFCI requirements in certain cases, it is prudent to implement additional safety measures to mitigate these hazards. These measures may include the use of corrosion-resistant receptacles and enclosures, the installation of physical barriers, the provision of ground fault monitoring systems, and the implementation of regular inspection and testing programs. Additionally, it is important to provide adequate training and education to personnel working in vehicle servicing areas to promote a culture of safety and hazard awareness. Examining the practical considerations of implementing GFCI protection in outdoor vehicle servicing areas, it is important to address potential challenges such as nuisance tripping, voltage drop, and equipment compatibility. Nuisance tripping refers to the unintentional activation of a GFCI device due to transient voltage fluctuations or electromagnetic interference. This can be a common problem in outdoor environments where electrical equipment is exposed to various sources of noise and interference. To minimize nuisance tripping, it is important to use high-quality GFCI devices that are designed to be less sensitive to transient voltage fluctuations. Additionally, it may be necessary to install surge protection devices to protect electrical equipment from voltage spikes caused by lightning or other disturbances. Voltage drop refers to the reduction in voltage that occurs along an electrical conductor due to its resistance. This can be a problem in outdoor vehicle servicing areas where long extension cords are often used to power equipment. To minimize voltage drop, it is important to use extension cords that are of adequate gauge for the amount of current being drawn. Additionally, it may be necessary to install additional receptacles or circuits closer to the point of use to reduce the length of extension cords required. Equipment compatibility refers to the ability of electrical equipment to function properly with GFCI protection. Some older or poorly designed electrical equipment may not be compatible with GFCI devices, resulting in nuisance tripping or equipment malfunction. To ensure equipment compatibility, it is important to use electrical equipment that is specifically designed to be used with GFCI protection. Additionally, it may be necessary to replace or upgrade older equipment that is not compatible with GFCI devices. When installing GFCI receptacles in outdoor vehicle servicing areas, it is important to follow the manufacturer's instructions carefully. GFCI receptacles should be installed in weatherproof enclosures to protect them from exposure to rain, snow, and other environmental elements. Additionally, GFCI receptacles should be installed in a location that is easily accessible for testing and maintenance. Regular testing of GFCI receptacles is essential to ensure that they are functioning properly. GFCI receptacles should be tested monthly by pressing the test button on the receptacle. If the receptacle does not trip when the test button is pressed, it should be replaced immediately. In addition to testing GFCI receptacles, it is also important to visually inspect them regularly for any signs of damage or deterioration. Damaged or deteriorated GFCI receptacles should be replaced immediately. Furthermore, it is important to keep GFCI receptacles clean and free from dirt, debris, and moisture. Dirt, debris, and moisture can interfere with the proper functioning of GFCI devices and increase the risk of nuisance tripping. In summary, implementing GFCI protection in outdoor vehicle servicing areas can present practical challenges such as nuisance tripping, voltage drop, and equipment compatibility. To address these challenges, it is important to use high-quality GFCI devices, minimize voltage drop, ensure equipment compatibility, and follow the manufacturer's instructions carefully. Regular testing and maintenance of GFCI receptacles are essential to ensure that they are functioning properly and to minimize the risk of electrical hazards. Evaluating alternative safety measures for electrical protection in vehicle servicing applications, several options can complement or supplement GFCI protection. Firstly, isolation transformers can provide a high degree of electrical isolation between the power source and the equipment being used. This isolation can help to prevent electrical shock hazards by limiting the flow of current in the event of a ground fault. Isolation transformers are particularly useful in situations where equipment is being used in wet or damp conditions. Secondly, ground fault monitoring systems, or GFMs, can provide continuous monitoring of electrical circuits for ground faults. These systems can detect ground faults that are too small to be detected by GFCI devices, providing an early warning of potential electrical hazards. GFM are often used in industrial settings where electrical safety is critical. Thirdly, equipment grounding conductors, or EGs, provide a low impedance path for fault current to flow back to the source. This helps to ensure that overcurrent protection devices, such as circuit breakers and fuses, will trip quickly in the event of a ground fault, minimizing the risk of electrical shock and fire. Proper installation and maintenance of EGC are essential for electrical safety. Fourthly, bonding is the process of connecting all metal parts of an electrical system together to create a common ground potential. This helps to prevent voltage differences between metal parts, reducing the risk of electrical shock. Bonding is particularly important in vehicle servicing applications where there are many metal parts that could become energized. Fifthly, personal protective equipment, or PPE, such as rubber gloves, insulated tools, and safety glasses, can provide an additional layer of protection against electrical hazards. PPE should be used whenever working with electrical equipment, especially in wet or damp conditions. Sixthly, training and education are essential for electrical safety. Workers should be trained to recognize electrical hazards, to use safe work practices, and to use PPE properly. Regular refresher training should be provided to ensure that workers stay up to date on the latest safety procedures. Seventhly, lockout/tagout, or LOTO, procedures are used to prevent accidental energization of electrical equipment during maintenance or repair. LOTO procedures involve disconnecting the power source, locking out the disconnect switch, and tagging the switch with a warning label. This helps to ensure that equipment cannot be accidentally energized while it is being worked on. Eighthly, arc flash hazard analysis is a method of assessing the potential for arc flash events in electrical systems. Arc flash events can release large amounts of energy, causing severe burns, explosions, and other injuries. Arc flash hazard analysis can help to identify potential arc flash hazards and to develop strategies for mitigating these hazards. Ninthly, infrared thermography is a non-destructive testing method that can be used to detect hotspots in electrical equipment. Hotspots can indicate loose connections, overloaded circuits, or other problems that could lead to electrical failures. Regular infrared thermography inspections can help to identify and address potential problems before they cause a failure. Tenthly, power quality monitoring can be used to detect voltage sags, swells, and other power quality problems that could damage electrical equipment. Power quality monitoring can help to identify the source of power quality problems and to develop strategies for mitigating these problems. In summary, there are many alternative safety measures that can be used to supplement or complement GFCI protection in vehicle servicing applications. These measures include isolation transformers, ground fault monitoring systems, equipment grounding conductors, bonding, personal protective equipment, training and education, lockout/tagout procedures, arc flash hazard analysis, infrared thermography, and power quality monitoring. By implementing a combination of these measures, it is possible to create a safe electrical environment in vehicle servicing applications.